Welcome to the Deep Dive. Today we're tackling a question that opens up a whole universe. What if prime numbers behave in a way that flips our understanding of order versus chaos?
Yeah, so our mission on this deep dive is to unpack this really mind-bending concept, prime numbers as reverse gerbes. We're going to explore how these primes connect with these super sophisticated geometric things called gerbes. And maybe surprisingly, how this links up to theoretical physics, think ADO-CFT, anti-de Sitter conformal field theory. It's about revealing arithmetic holography. Okay, let's dive in.
It's fascinating that this whole framework makes you rethink order and chaos. We usually think chaos is messy, but this suggests it can be a key ingredient in a system that's actually deeply ordered underneath. It's almost like looking at something familiar in a mirror, seeing its opposite.
That's a great way to put it. So let's introduce the main players here. Gerbes and prime numbers. First up, gerbes. Now, if you haven't heard of gerbes before, don't worry. Think of them as these really sophisticated geometric structures. They're locally smooth, which means if you zoom in, everything looks normal, like a flat piece of paper. You can lay down one small tile, no problem.
Right, when you try to glue these smooth local bits together globally, they don't fit perfectly. There's this inherent twist or obstruction. It stops you from making a perfectly smooth global thing. It's a bit like trying to tile a curved surface, like a sphere, with flat squares. Locally, one square is fine, but try to cover the whole sphere smoothly. You can't. You get these points where things bunch up or don't meet. Mathematically, this global problem is captured by a Dixmeyer-Dewey class.
Okay.
It lives in higher cohomology, specifically H3, and it comes from problems in what are called triple overlaps, where three local pieces try to meet. Think EC. So local perfection, but global brokenness, a gap you can't fix.
Okay, got it. Prime numbers, 2, 3, 5, 7. Indivisible building blocks. What's captivating is how they behave. Locally, their distribution seems chaotic. There's no easy formula to predict the next prime. Think about prime gaps. Sometimes they're small, sometimes huge. It looks random up close.
Yeah, it does. But despite that chaos, primes impose perfect order on all numbers globally. That's the fundamental theorem of arithmetic. Every whole number bigger than 1 breaks down into a unique set of primes. Then you have things like the prime number theorem. It tells us broadly how primes thin out as numbers get bigger, roughly like x divided by log x.
Right.
And the Riemann-Zeta function, that's like the master key. It has this amazing property, a functional equation, that reveals this deep symmetry in how primes are distributed overall. Even though they seem random one by one, the zeta function sees the grand pattern. It's like a global GPS for primes.
We have gerbes. Locally neat, globally messy.
And prime.
Locally messy, globally neat. This is where it gets wild. Your sources suggest this idea. A prime number is like a reverse gerbe.
Exactly, that's the big conceptual flip. A normal gerbe is locally smooth, globally twisted. A reverse gerbe is the opposite. Locally chaotic, unpredictable, but globally coherent. It's a mirror image.
A standard gerbe is like a smooth map that wrinkles when you fold it. And a reverse gerbe is like a pile of random scraps that when you step back somehow form a perfect picture. That's quite an inversion.
Precisely. You might ask, how do we pin this down mathematically? We can make a table. Gerbes. Local consistency, yes. Global consistency, no. Result. A non-zero obstruction. Primes. Local consistency, no. Unpredictable gaps. Global consistency, yes. Unique factorization. Result. Effectively zero obstruction globally.
Okay.
Analytically. Gerbes show problems in triple overlaps, the H2 cycles. Primes show global order through things like the analytic continuation and functional equation of the Riemann-Zeta function. That really demonstrates their underlying coherence despite the local randomness.
But we set up this intriguing reverse gerbe idea for primes. How do we connect the chaos of primes to the geometry of gerbes? Your sources say there is a shared mathematical pattern, a scaling law that acts as a translator between them.
They talk about arithmetic holography, analogous to AS-CFT correspondence in physics, a kind of holography. In this arithmetic version, the primes, with their discrete, chaotic nature, act like the boundary of this mathematical universe, the edge of some complex space.
Okay, the primes are the boundary.
With their built-in twists and obstructions, they represent the bulk curvature inside that space. And the bridge, the fascinating connection, lies in a shared mathematical pattern, a scaling law. This is the deepest insight. The same logarithmic scaling laws, 1 over log x, shows up on both sides. It's like their shared mathematical signature.
1 over log x.
On the prime number side, log x tells us about the density of primes, how they thin out. You could almost think of it as measuring the entropic profile of the primes, how much randomness or unpredictability they carry locally.
And on the side,
On the Gerbes side, that same one-log scaling is related to quantifying the curvature or the obstruction amplitude. How strong is that global twist? Finding the same scaling law as an invariant across different mathematical structures is rare. It suggests the, let's say, rate of complexity growth or information growth follows this logarithmic pattern on both sides of this arithmetic geometric picture, which implies this sort of decelerating change, a kind of deep structural memory built into both systems. It's common rhythm.
This primes as reverse Gerbes thing sounds abstract, almost philosophical. But is there a way to see this, a tangible, maybe even visual example?
Absolutely, and that's crucial, right? It's not just abstract noodling. The sources point to a concrete geometric object called the dynamic prime Cantor set, or DPCS. It's this really cool fractal construction built on the simple unit interval, just the line between 0 and 1.
A fractal, how's it built?
It's made by iteratively removing pieces of the interval. The key is the removal process is dictated by the prime numbers. At each step in the construction, you use the kf prime number, let's call it pk, and remove sections based on all the primes up to and including pk. The primes are carving out this shape step by step.
How does that show the reverse Gerbes thing?
It embodies it perfectly. The removal pattern at any given step is unpredictable unless you know the entire sequence so far. You can't look at a small piece and know what's next. That's the chaotic local unpredictability.
Right. Globally.
Globally, the DPCS has amazing properties. Its total length, what mathematicians call its measure, actually shrinks to 0. So technically, almost nothing is left. But here's the kicker. Its dimension is proven to be exactly 1.
Dimension, even though the length is 0.
Dimension 1 means it's still as complex as the original line segment, even though it's full of holes and has no length. It stays perfect, compact, totally disconnected, yet fills space in this dimensional sense.
Right.
And here's the real connection, the sort of smoking gun. The proof that the DPCS has dimension 1 relies heavily on deep results from analytic number theory, specifically the prime number theorem. It shows how global properties of primes, encoded in the zeta function, manifest geometrically. It's tangible evidence that global coherence can emerge from local chaos, just like the reverse Gerbes idea predicts.
If arithmetic can have this kind of geometric, almost holographic structure, where else might this idea lead? Does it stop at numbers and geometry? Your sources seem to hint at something broader.
The framework extends potentially into the structure of knowledge and reasoning, which is ambitious. The sources propose that hyperbolic space is the best to represent categories.
Why that specific kind of geometry?
Categories describe abstract structures and relationships, like networks of concepts or fields of study, and how they link together. Often these systems show what's called an exponential growth of morphisms. Basically, the number of connections or possible pathways as the system gets bigger or more detailed. That kind of exponential growth is characteristic of hyperbolic space. Volume in hyperbolic space grows exponentially as you move outwards.
I see the parallel.
In negatively curved hyperbolic space, paths that start close together tend to diverge very quickly. This seems to mirror how, in logic or reasoning, tiny differences in initial assumptions can lead to vastly different conclusions. Think about different philosophical systems branching from slightly different starting points.
Okay, that makes sense. You mentioned compression.
Hyperbolic geometry has this property where you can embed complex, deeply nested hierarchies into a compact space, visualized as a disk, like the Poincare disk model. This suggests a model for how our minds handle or navigate huge amounts of interconnected, abstract information without getting lost, a way to compress complexity.
So the implication is that maybe reasoning itself is like finding a path through this abstract, curved space of ideas.
That's the provocative idea, like taking a geodesic block, the most efficient path, through a hyperbolic categorical manifold. This loops back to something you explored in episode 15, visualizing the Cantor set in hyperbolic space. That visualization, in a way, was setting the stage for this understanding how discrete, disconnected structures, like primes or the gaps in the Cantor set, can be mapped onto a continuous geometry with curvature and flow, like categories potentially in hyperbolic space. It's suggesting a geometry for thought.
I can hear some listeners thinking, this is sounding grand. Connecting number theory, geometry, physics, thought. How do we know this isn't just finding appealing patterns or stretching metaphors too far? Skepticism is natural with these big leaps. And the sources do seem to anticipate and address some of that pushback.
One common point of skepticism is this recurrence of logarithms. Are we just conflating logarithms found in different fields? The argument isn't that it's the exact same logarithm doing the same job everywhere in prime density, machine learning convergence, in how we perceive stimuli. Rather, they might belong to a family of scaling behaviors. They all reflect some underlying principle, maybe related to information bottlenecks or efficient coding or hierarchical processing. It's about a shared type of scaling, not identical functions.
It's about the pattern, not the exact instance. What about the AutoX formula itself? Critics might say that's a common approximation, pops up lots of places.
And that's true. It is a known asymptotic form. But the key question in this context is why it appears where you have this interplay of local randomness and global order. The proposal elevates it beyond common formula. It's suggested as potentially being like the metric tensor of this duality, the thing that fundamentally measures the relationship, the scaling between the prime boundary and the Gerb bulk. It's given a more structural role than just coincidence.
And the charge that it's maybe just poetry until the math is nailed down, like arithmetic, add SCFT.
The sources acknowledge the formal functor, the precise mathematical machine linking these worlds, is still under construction. That's ongoing research. They frame this not just as poetry, but as epistemic holography. It's a blueprint for a potential general theory of duality, one that could apply across different ways we represent knowledge. So it's presented as a research program, a hypothesis generator, aiming to guide the development of rigorous math, rather than just describing existing math.
And crucially, it's not all abstract theory. Your sources point to an empirical anchor, right? A real-world experiment.
Yes, this is important for grounding the ideas. They mention a reinforcement learning experiment using a twisted chain. In this setup, they observed that an AI agent's probability of failing to reach its goal seemed to grow roughly like one lone, where Karin was related to the complexity or length of the chain. That's the same scaling law we saw with prime density.
Just the scaling law?
They designed a special topology-aware RL agent. This agent had essentially built-in knowledge about the possibility of obstructions, kind of like being aware of gerbes. This topology-aware agent significantly outperformed standard RL agents, specifically in environments that did have these known cohomological obstructions, these twists. So it's tangible evidence. It suggests that understanding these higher geometric concepts provides a real advantage in navigating certain complex systems. It's like a tiny experimental proof of concept, a microhologram supporting the bigger theoretical picture.
The full mathematical machinery, like the reverse Gerbes functor, that's still being built. But the framework offers testable ideas and points towards real phenomena in AI. It seems like a move from maybe mathematical mysticism, as some might see it, towards what the sources call mathematical archaeology, actively digging for these fundamental structures. So let's recap. We took quite a journey today, from the local chaos but global order of prime numbers, leading to this idea of reverse Gerbes. We explored this concept of arithmetic holography, where primes are like the boundary and gerbes are the curved bulk, connected by that one long scaling law. We saw this embodied in the dynamic prime Cantor set, a fractal built by primes, and touched on how hyperbolic geometry might be the natural space for categories and structuring thought.
It ties together seemingly disparate areas. If the bedrock structures of arithmetic, primes and sophisticated geometry, are linked by logarithmic scaling, and if reasoning processes might unfold in a space that has a hyperbolic categorical nature, what does that suggest about the underlying shape, the unseen curvature of reality itself, and how we perceive it? Your brain perceives the world using logarithms, logarithmic harmonics.
Harmonic logarithms are specific mathematical functions. Think of them as special relationships that generalize ideas like the harmonic series, musical overtones, and harmonic numbers too. They just pop up everywhere. Summing infinite series, building algebraic structures for research. They're really fundamental building blocks in fields like analytic number theory, analysis, even combinatorics, the math of counting things.
Okay, they're foundational math things describing proportions. But the interesting part for me is how this math harmony shows up in the real world, like in music.
Yeah.
When we talk logarithmic harmonics, it's not your typical scale, right?
In music, logarithmic scales are non-Pythagorean systems. Different from traditional music, think about zooming into a fractal. You see similar patterns at every scale, but the scale itself is changing logarithmically. That's kind of how your brain handles the massive range of sensory input without getting totally overloaded.
Our brain is wired for these proportional relationships. Why? Why that? Instead of just simple linear perception.
Efficiency, basically. It's all about efficiency. Neuroscience keeps finding these log patterns everywhere. It's not just quirks. Your hearing, for instance, sound intent, measured in decibels, logarithmic scale. Vision. Brightness perception follows a log curve too. And memory. Remember that forgetting curve example. Super fast loss at first, then it levels off. These aren't accidents. The brain processes a huge dynamic range of information. And what's really fascinating, Some researchers even suggest that maybe moments of awareness, insights, might flicker along similar logarithmic patterns, subtle shifts we don't consciously register.
If our biological brains do this, what about artificial brains? How does this logarithmic thing play out in AI, especially reinforcement learning?
Here's a remarkable fact. Pretty much all reinforcement learning, or RL algorithms, operate using the logarithm of probabilities. It's not just like a handy shortcut. It seems to be a mathematical necessity. It reveals this really deep connection between natural and artificial intelligence.
A necessity. You mentioned numerical instability and vanishingly small values. The AI can't compute the numbers. If they don't use logs, they disappear.
It can be catastrophic for learning. In RL, the AI is dealing with probabilities of taking actions, probabilities of outcomes. If you multiply lots of these tiny probabilities together directly, the numbers get incredibly small. The computer rounds them down to zero. That's called numerical underflow. But you know the math rule, taking logarithms turns multiplication into addition. Log P1 times P2 becomes log P1 plus log P2. That simple transform, it prevents the underflow, it keeps the calculation stable, accurate. So modern RL algorithms, teaching robots, playing games, whatever, they all work in this log probability space. It makes the whole learning process stable and actually feasible computationally.
We see this in practice, right? AI researchers talking online. I remember sources where people on Twitter are constantly talking about how crucial log probabilities are for their algorithm, updating an AI based on reward times the gradient of the log probability of an action. Or language models using the sum of log probabilities in their reward functions. It seems to be everywhere.
Exactly right. Practical examples underline the deep connection. It doesn't matter if it's biology or silicon. Intelligent systems gravitate towards logarithmic space. It comes down to Shannon's information theory, measuring information in bits, which is logarithmic, plus efficiency we talked about, handling huge ranges, and numerical stability that makes complex learning actually work.
Logarithms are in math, music, our brains, AI. The big aha was this idea of scale invariance. That seems to be the thread tying it all together, doesn't it?
Scale invariance is key. It means a system or a function keeps its essential form, its core properties. Even when you scale it up or down, multiply it by a constant. Think of zooming in or out. The structure looks the same. Mathematically, the natural logarithm function itself is the classic example. Log of lambda times x just equals log lambda, log maximum. The form is preserved. It just shifts by a constant amount. Harmonic logarithms often share this kind of property, and we see it everywhere, which is kind of amazing. In that logarithmic music scale, if you transpose it, multiply all frequencies by the same factor, like going up an octave. The relationships between notes, the intervals, stay the same. Our hearing works like that too, focusing on the ratios. In image recognition, there are filters, logarithmic radial harmonic filters, to spot patterns no matter how big or small they are. They use a log transform to achieve that scale invariance. And maybe most profoundly in pure math, the distribution of prime numbers follows a scale invariant law, roughly x over log x. The chance of a number around x being prime is about 1 over log x, and this pattern holds whether x is huge or small. There's no typical size for primes. Even the Riemann hypothesis about the zeros of the zeta function, which encodes prime locations. Those zeros are thought to lie on a line defined by logarithms. It suggests primes have this weird mix of randomness and perfect logarithmic order, chaos and harmony.
Wow.
If both our brains and sophisticated AI operate in this logarithmic space, it might explain why some AI behaviors feel surprisingly natural or intuitive.
From the abstract beauty of prime numbers to the music you're listening to, even your smart toaster, everything on some level is grooving to the same logarithmic beat.
If all these different areas, prime numbers, hearing melodies, brain function, AI learning, all seem to run on this fundamental logarithmic rhythm, what does that tell us about the deep down nature of reality itself? About what intelligence is?
Definitely something to think about. For anyone wanting to explore more, mathematicians delve way deeper into harmonic logarithms, infinite series. Musicians, composers, maybe try experimenting with these logarithmic scales, see what sounds can create. And AI researchers keep exploring those log probability spaces. Who knows what emergent properties might arise? It feels like the journey into this logarithmic universe is just getting started.